Had some fun. All right, Apple time is almost 8 o'clock. As I mentioned, y'all are here at 5. I don't want to have to wait till 5:05 because why do we wait for other people to start when we're already here, right? If they want to catch up, they'll know how to catch up because that stuff will be posted. That clock says 5. That clock says 5. We're calling it 5. Hey, good evening. Thanks for coming out. It's Module 8. So we have 4 more modules before the end of the semester. Module 8, Module 9, 10, and 11. And we're going to start to see with some of the basically second half of this section, we're going to start to see some problems that do revolve around the same sort of thing, where I'll give you one scenario and I'll ask you a number of different questions that are all from a similar scenario. If you've had an opportunity to look at these homework problems, you'll see exactly what I'm talking about because we'll have basically the same population mean, same population standard deviation, the same sample size. Those last two together mean it's the same standard error. We all right out there? It's a pole, Leah.
What?
It's a pole. You get stuck in the door?
Yeah, I'm not the only one.
Oh wait, is the door just all
Yeah,
locked? All right, well, let's remedy that.
we put something in.
Oh, thank you. Appreciate that.
Yeah.
I was gonna ask you to take over for a while, Ted, and then I'll just do it myself. All right. Sorry about that. I was wondering where you were. Cool. 5 o'clock. Let's start. Question number 1. 1 out of 49. What happens to the standard error of the mean if the sample size increases? Send that to the projector. Standard error of the mean. What's the symbol for standard error of the mean? The symbol, Stephen.
Sigma with an X bar.
Sigma sub x bar. And how do you calculate that value? What's the formula?
Calculation.
Hey, Katie, how do you calculate standard error? Too soon. Get your coffee. How do you calculate standard error? Stephen.
Is it sigma squared from a sigma over a square root of n?
Yeah, sigma over square root of n. Or if you're doing it for the sample mean, it's s over square root of n. So what happens to this value as this value gets bigger? As the denominator of a fraction gets bigger, the entire fraction itself gets smaller. So answer to question number 1. What happens to the standard error of the mean when the sample size gets bigger? Sample size, or the standard error decreases as sample size grows. 1 down, 48 to go. Number 2, what happens to the distribution of the sample means if the sample size is increased? Again, this goes back to those blue dots. Each one of those blue dots in that simulator represents, oh, don't, all right, nice. So I can actually go to that thing as opposed to talking about it, I can show you. I can try to go to that thing. Question 2 says, what happens to the distribution of the sample means if the sample size is increased? So, what happens to the distribution of the sample means as the sample size is increased? What happens to the blue dots? Chris? More normal, and what else? And what else? Mike?
Get smaller.
Get smaller. Let's call it narrow. Let's see what the question asks. Yeah, so let's actually do this. Yep. Looks like it's, well, that's not bad, but if, let's say this one was not normal, yeah, we definitely get more normal, and it becomes more narrow. So question 2, what happens if the sample size is increased? The distribution of the sample means becomes more binomial. That seems silly. It becomes more normal. That sounds like what Chris said. Becomes more, that's not poison, that's Poisson. No, it definitely becomes more normal. 2B. 2 down, 47 to go. 3 of 49. When using the distribution of sample means to estimate the population mean, What is the benefit of using larger sample sizes? So the fundamental question of statistics, why is a bigger sample size better? We've got three options up here. The shape of the distribution becomes narrower since the dispersion is less, and estimates of the mean are less precise. The shape of the distribution becomes narrow since the dispersion is less and the estimates of the mean are more precise, or the shape of the distribution becomes narrower since dispersion is more and estimates of the mean are more precise. I got same three hands. Let me go to Aaron.
Shape of distribution goes narrower since dispersion is less. Estimates of the mean are more precise.
Yeah, this one right here. That's effectively the same thing. Good call. Good answer. Thanks, Aaron. It's effectively the same thing that we're talking about here. The distribution becomes narrower so that these estimates, remember they're estimates because they're based on the probability of actually observing those particular values. Those estimates become more precise. In Module 9, we're actually going to create interval estimates, confidence interval estimates, our best guess as to what mu is by using standard error and z-scores and point estimates, x bar and p. Yeah, we're still using the same set of vocabulary, which is why for many of you, the first thing I said was vocabulary. P, pi, x bar, mu, z, sigma, n, s, and again, 3 down, 46 to go. Hey, let's start actually working on a problem here. That trucking company claims that the mean weight of its delivery trucks when they are fully loaded is 6,000 pounds with a standard deviation of 150 pounds. Assume that the population follows a normal distribution. 40 trucks are randomly selected and weighed. Within what limits will 95% of the sample needs occur? How do we go about approaching this problem? Any ideas? Watch step, Joe. How do we go about approaching this problem? Stephen, talk to me. What do you think?
Well, it says it's asking for 95%. So 95% is 2 standard deviations.
Roughly, go on.
So if that's what 95% is, then 1 standard deviation is 150 pounds.
Okay.
So if you have 2 standard deviations, should be 300 pounds.
Okay.
And then
So-
you're plus or minus that.
All right. So in this case, we need to first extract what some of the important information is here. So Steve's mentioning the standard deviation is 150 pounds. We know that the mean is 6,000 pounds because both of those things are given to us. We know that 40 trucks are randomly sampled here. So we got 40 trucks. Now I understand if you have a single truck, that single truck might be off by, say, 300 in one direction and 300 in the other direction. Now that's for a single observation. But if we have 40 trucks, our understanding is that some of those trucks are probably going to be above 6,000 and some of those trucks are probably going to be below 6,000. And if I have 40 of them, given that it's normally distributed, some of the ones which are above will probably cancel out some of the ones which are below. So in this circumstance, going right to 5,700 and 6,300, that would be a good estimate for a single truck. We know 95% of single trucks goes there. But we actually got to go a little bit deeper. We know that in this problem, the population mean of all trucks is 6,000 with a standard deviation of 150. Now this is similar to the way the exam questions were asked for vocabulary here. We didn't say that we went out and sampled 40 trucks and found that the mean of those 40 trucks is 6,000 with a standard deviation of 150 or wherever I should be pointing. That's not what we said here. The first sentence, the first statement says that this trucking company makes this claim. And if the trucking company makes the claim, then it is said to be true. Until you observe it yourself and say, I went out and took a sample and observed this, that's when you go ahead and use your sample means. Otherwise, if they're just telling you that the mean is 6,000 and the standard deviation is 150, you put them as population values. But N in this case is 40 because we observed 40 trucks. We're still going to go to a normal distribution. We're taking a sample of a normal distribution so we can work under those auspices. The raw mean is 6,000. And I know that the z-score of the mean is always 0. I know that to be true always. But because I'm talking about 40 trucks, there's something else I got to compute in the interim, Chris, and what's that? We don't have X bar. We don't have a sample mean here. X bar is not given here. If it was, I'd say I took a sample of 40 trucks and found that those 40 trucks had an average of 6,024 pounds or something like that. And I'd want to compare that to the other way. But I still want to do something like Stephen mentioned, which is something to do with kind of like the empirical rule where I know 95% of all observations are going to fall within 2 standard deviations of the mean. And it looks like this. If I put 95% of my stuff in the middle of this normal distribution, I can go out a certain direction to the left or to the right, below and above this population mean, and I'll cover 95% of means of a particular size. But I can't go out using the standard deviation because that's individual trucks. This question is asking me, within what limits will 95% of the sample means occur? So I'm going to find sample means of what size? If I'm going to take a sample mean, I have to take a sample. And that sample has to have some size. The size could be 1, but what is the sample size that's specified in this particular problem? Katie? 40. So I'm going to have sample means of size 40. We know that if those sample means were only of size 2, there's a lot of dispersion. We can think about those blue dots as being very wide. But those sample size, the sample size in this case is 40. So I need to compute my standard error, which is sigma over square root of n. 150 over square root of 40. Anyone happen to know this one off the top of their head? Square root of 40 is going to be 16, 14, 4, 2, square root of 20, 75 over square root of 20, square root of 25, 3, 75 over 4 and change should give me something on the order of 15-ish, 20-ish. What do you got? Katie, what do you got? 6.32. Confirmation? 150 over square root of 40, 6.32? 50.
That was just the square root of 40.
Oh, square root of 40 is 6 and change. All right. 150 divided by 6 should give me something around 20 and change. Chris, what do you got? 23.73. Confirmation there, 23.7. All right, I see thumbs. So now my standard error is something on the order of 23.7. We can look back at our here. Look back at our question. We know we're going to be working in some sort of round numbers here. We know that this case is the wrong case, that 5,700 to 6,300 is far too wide. In this case, we're going to 54, which appears to be about 46 above or below. That looks interesting. because the next one, correct. I was just going back to take a look at my answer options to see how 24 might play into this. But let's complete this problem. What we're looking for are, in fact, these raw scores. So if we're working something like this, we start with the proportion of 95%. 95% is going to be between those two boundaries, which means those areas, if you divide 95% in half, is 0.4750. Divide 0.95 into 2, we're going to have 47.5% on one side, 47.5% on the other side. So once we have those areas, we can go to our z-score table, and hopefully, if Stephen is correct, my z-score table is going to get me a value of somewhere around 2. All right, you know what the answer is. I can't find the table. There's the table. So for a z-score of 1.90123456, you start in the middle here, look for 0.4750, because that's the value which is in my area, which looks like my picture. 0.4750 corresponds to a z-score of plus and minus 1.96. And then if I take my mean of 6,000 and I add 1.96 times my standard error, or I take, let's make that minus 1. In this case, I have two options. I can go, let's make sure. To find the two bounds up there, I start with my mean of 6,000, and I take the z-score that I found of negative 1.96. Put that into the formula, multiply it times my standard error. So 2 times 24 is roughly 48. So I'm probably going to subtract about 48 from the mean. On this side, 6,000, and I add 1.96 times my standard error. So roughly 2 times 24, again 48. I'm going to be adding or subtracting approximately 48. No. Adding or subtracting approximately 48. So I get something around 60, 48, and 60, sorry, something around there. Assuming my math is correct, which it isn't always. That's why I have Excel. Oh no, I don't see anything here that says 59, 58, 59, 52, and 60, 48. But I see something that's very close to it, which is 59, 54, and 60, 46. And I bet if you use 1.96 and 23.7, I bet you get the exact answer for A. Tap and check. So let's take a step back and try to just walk through the different parts of this process real quick, because this is the one type of problem that none of the classes have done yet. But it's still the same process of being given some proportion. In this case, the question asks, 95% of all sample means fall between what two values? And once we establish that the proportion is 95%, it needs to fall between what two values? That's working from a proportion to a raw score. That proportion, 95%, allowed me to put 47 or 0.4750, 47.5% on either side of the mean. That's my area, 0.4750. I went to my table and turned that 0.4750 into a z-score, which is plus or minus 1.96. And then I used that formula, x equals mu plus z times sigma. In this case, x equals mu plus z times the standard error, sigma sub x bar, in order to find my lower bound, 6,000 minus 54, and 6,000 plus 54. It's the same process we've been doing in Module 8, except we're using standard error instead of standard deviation. Question number 5. Oh, wait. What's our answer? Question number 5. In a certain section of Southern California, the distribution of monthly rent for one-bedroom apartment has a mean of $2,200 and the standard deviation is $250. Grasp that for a moment. The average is $2,200. That's the average. Some apartments are going to cost less than $2,200. Some apartments are going to cost more than $2,200. How much more or less? Well, the standard deviation is $250. However, the distribution of monthly rent does not follow the normal distribution. The population is not normally distributed. That could cause some problems. In fact, it is positively skewed. Palm of your right hand, positively skewed. Means most of them are on the lower side, but a couple of them are really expensive. So that means there's a couple of apartments in Southern California which may be pulling the mean that way because someone's paying 10 grand a month, but mostly people are on the left-hand side of that picture. What is the probability of selecting a sample of 50 one-bedroom apartments and finding the mean to be at least $1,950 per month? This question is going to ask us about what the probability is. So we're going to work from a raw score, in this case, 1950, to a probability, which is going to be our answer. If this were a standardized test, and some of you are going to take GREs, some of you are going to take GMATs, and some of you are going to take LSATs, and et cetera, et cetera. I don't know. I sort of ran out of them. Look at your answer choices. Those answer choices might lead you to believe there is something strange going on with this problem. We're going to execute it mathematically, following the process that we've been working on. But we're also going to revisit why you should be able to sort this out right away. First of all, can this answer be determined? The population of apartments is not normally distributed. Does that mean we can't answer this question? Yes or no, and why? Wants to take a crack at it. Can we answer this question? No. I mean, I want to know if I can eliminate the answer choice cannot be determined. My concern is the population is not normally distributed. Does that mean I cannot move further because my population is not normally distributed? Or is there something that allows me to move forward? Mike.
You can actually solve it because it gives you a sample size.
So
So you can use the sample, you can formula to find. It gives like a picture of like what the population might look like using sample size.
getting there. Getting there. Anybody? I appreciate that. I do appreciate that. That's good. Because we've got a sample size, and that's important. That's important. One of the corollaries of the central limit theorem, and that's something that we discovered when we were doing all this blue dot nonsense, is that even if you start with a positively skewed distribution, like for example, the rent for apartments in Southern California, and you take a sample of sufficient size, those sample means are normally distributed. So we can still work with sample means because those means are normally distributed. In the case of this problem, let me make sure I have all the essential information here. And I'm going to write that down. We have the apartments have a mean of 2,200, a standard deviation of 250, and we want to know if we have a sample of 50 apartments where the average is 1950. So that's the information that we're provided about this problem. Is that the mean is 2,200, it's positively skewed around with a standard deviation of 250. We're going to ask a question giving us a raw score of 1,950, but based on a sample of 50 apartments. We're trying to find the likelihood of finding 50 apartments whose average rent is 1,950 or more. We can draw a normal distribution to answer this question because the sampling distribution as sample means is going to be normal. Even though this says not normal, we can draw a normal distribution because the central limit here. Mu is in the middle, that's 2,200. Z-score for the mean is here. Somewhere over here is that mean of 1950. Now I want to know what the probability of finding greater mean of 50 apartments greater than 1,950. We've got to go from a raw score to a z-score to an area, and an area to a proportion. In this case, we've got a raw score of 1,950. I got to calculate z-score. What's my formula for a z-score? I want 5 or 6 words. 5 or 6 words. I'll try to get this right. I apologize every time. Thank you. 6 words. Sampling error divided by standard error. Sampling error is x bar minus mu, and standard error is sigma over square root n. But our z-score is sampling error over standard error. And our sampling error here is x bar minus mu, and our standard error is sigma sub x bar, or sigma over square root n. What is my sampling error in this problem? Value from our sampling error? Chris?
1950 minus 3.
Otherwise known as?
Negative. 260.
Yeah, I think it's 250. Okay. sigma 7x bar. We calculate that. Sigma over square root of n. 250 square root of 50. What do we get there? What do I get for a standard error here? We want to hop on? Hey? Okay.
35.36.
35.4. Anybody confirm 35.4? You know what? It doesn't matter if it's 35.4 or just 35. Because this is a z-score. And our z-score, sampling error over standard error, this is a very large sampling error relative to that standard error. That looks like it's on the order of 7. What's 250 divided by 35? Remember, it's negative. That's a z-score. A z-score of -7. If that doesn't make you uncomfortable, you've forgotten about what z-scores are. Z-scores bigger than 2 or smaller than -2 should send up red flags. If I calculated that value, I'd be suspicious as well. But remember that this is California. And although they are not normally distributed rents of apartments, that is, they do average around 2,200. And we're asking the question, what's the likelihood of finding 50 apartments whose average is 1,950 or greater? 50 is a pretty large sample size. I really expect if we find 50 apartments that their average is probably going to be somewhere around 2,200. If you take a sample of 50 things from a population, your sample mean should be close to your population mean. How close? Well, certainly a lot closer than 1950. With a z-score of -7, I don't even need to go to the table. I can. If I go to the table, it only goes as far as 3.9 and tells me the area is 0.5. So, what proportion of samples of 50 apartments are greater than 1,950 as a mean? Or what's the likelihood of finding 50 apartments and their mean is greater than 1950? The shaded area on our picture. Yeah, 1 or 100%. If you take a sample of 50 apartments in Southern California, it's guaranteed that the average is going to be greater than 1,950. Five down, 44 to go. An experiment involves selecting a random sample of 256 middle managers for a study. That's awesome. Do you know why I like studies with 256 subjects?
Square root.
Yeah, because the square root of 256 is 16, and I know I'm going to have to take the square root of the sample size for my standard error. One item of interest is their annual income. The sample mean is computed to be 35,420, and the sample standard deviation is 2,050. So I have X bar and I have S. What is the sample standard error of the mean? Aha, you know why I also like this question? Because it's easy. How do you calculate the sample standard error? James, carry this one, please.
X bar minus 3.
That's sampling error. I
Oh,
need
wait,
standard error.
My bad. It's S over the square root of n.
S over square root of n. Very good. So in this case, even though they tell me the sample mean, I don't care. Because all I need is sigma. All I need is S and n. And I can take 2050 and divide it by 16, and that will get me S sub x bar, otherwise known as the sample standard error of the mean. Remember how I got all pedantic when I would say sampling error, and then I'd be like, what's x bar minus mu? And people would be like, that's sample error. And I'd be like, no, it's sampling error, not sample error. Here's a reason why. It's because if you see sample standard error, your mind might go to, ooh, I see that word sample, and that indicates to me it should be that x bar minus mu thing that's really easy to calculate. Sample standard error means S sub x bar because you're using the sample standard deviation. And all you got to do here is take 2050 divided by 16, which seems like it would be something around 500 over 4, which sounds like it's about 125. We got something like that up here. My guess is this one. Is that what you computed? Confirmation?
Why was it 16?
Because, yeah, let me not be a jerk about this. Good call, Aaron. In this case, it tells me that the sample mean is 35,420. The sample standard deviation is 2,050, and my sample size is 256. The question asks me, what is the sample standard error of the mean? Which is S over square root of n. 2,050 divided by the square root of 256 is 2050 over 16.
Yeah.
And then I looked at that and said 2050 is approximately 2,000. And I know 2,000 divided by 4 is 500 over 4. 500 over 4 is 125. So I'm looking for an answer around 125. As it turns out, there is an answer around 125. It's 128. That's because I don't have a calculator. Because calculators are for students. When I was a kid, I was told I wouldn't be walking around carrying a calculator in my pocket everywhere I went. That's right, because I carry Excel in my backpack. You guys are tough today. You're ready for Easter, aren't you? You were ready for a snow day this morning, weren't you? Yeah, I'm in that club too. Don't you? I had to clean a car off this morning. How did I do that? You're also concerned that we're only 6 problems in, and it's 5:37. That's all right. We can get snappy. Suppose a research firm conducted a survey to determine the mean amount a steady smoker spends on cigarettes during a week. A sample of 100 steady smokers, and I'm happy that it's 100 steady smokers. Why am I happy it's 100 steady smokers, James?
The square root of 100 is that.
Yeah, that makes math super easy. A sample of 100 steady smokers revealed that the sample mean is $20 and the sample standard deviation is $5. What is the probability that a sample of 100 steady smokers will spend between $19 and $21? We're moving from raw scores to proportions or probabilities in this case. I'm going to extract some of the essential information first. Actually, you can help me extract some of the essential information. What's some essential information here in number 7? Who's got some stuff I should pull out? Chris, thank you, sir. Don't hurt your back carrying us today, please. N is 100 because there's 100 observations. What else do we got? Standard deviation. Sample the population. Okay, good. Is 5. What else do we got? Katie.
Sample mean is 20.
X bar is 20. Very good. Those are the 3 pieces. This is all information, by the way. In this case, N, S, and X bar. Sample size, sample standard deviation, sample mean. All pieces of information that I observed. And now we're going to ask the question, what's the probability of finding a sample of 100 steady smokers who are between, what's the probability of finding between $19 and $21 as their average weekly spend? Normal distribution. Thank you, central limit theorem. Mu is in the middle here at 20, and its z-score is always 0, and I'm sure of that. Somewhere between 19 and 21, this area is our answer. How do we get from a raw score to a proportion? We need a z-score, an area, and that's how we get to proportion. Not trying to go super fast, it's that we've established this and been doing these types of problems for about 2 or 3 weeks. It was material that you were asked to master for the midterm, and many of you did. So I just need to go from a raw score. In this case, I could choose either one of these. Both of them are equidistant away from the mean. So if I find a z-score for 21, it's the same as the negative z-score for 19. So I'm just going to go with 21 because it's on the positive side. I need to go from a raw score to a z-score. What's my formula for a z-score? Katie?
Sampling error over standard error.
5 words. Sampling error over standard error. All right, what's my sampling error? If I choose 21 as my target, what's my sampling error? 1. Yeah, what's my standard error? By the way, who's already got the sampling error in their head? Who knocked that out? Because I saw those numbers were super easy. S is 5, N is 100. Thanks, Joe. Appreciate that. Yep. So our z-score is sampling error. By the way, I'm now going to stop writing the word error at the end because I'm tired of writing those 10 extra letters every time. Sampling error over standard error. Sampling error over standard error. X bar, well, so in this case, 21 is what we're looking at because that's our guess. Minus 20 divided by our standard error, which is sigma sub x bar is 5 divided by the square root of 100. 5 over 10 is 0.5. Two. I mean, I think that's right. I hope that's right. I haven't looked at these problems in 4 months. That's why I have to be quality assurance. You guys wonder why I'm always so concerned about procedures, because I don't have the opportunity to be wrong. Because if I'm wrong right now, you have no idea how embarrassing that is. Maybe you do. You know all those fears of public speaking that you have? Imagine your entire credibility is based on your ability to answer questions right each and every time you're in front of the audience. And you say something wrong, and everybody looks at you like you're stupid. But when you're doing that in a normal public speaking situation, no one really cares because most people in your public speaking class are already thinking about what they're going to do on the weekend. But in this case, when I get the feeling that you actually think I'm stupid, it's because I've demonstrated my stupidity. That's why I have to follow processes by writing the problem the same way each and every time so that I don't actually get verification when I make a mistake. That internal dialogue that says, Jeff, you're stupid. 50 faces looking back at me, which I'll go, Jeff, you're stupid. Anyway, I think the answer is 2. I took that raw score of 21, converted it to a z-score of 2. I'm going to come to this area, come to this table, and find that my area is 0.4772. What should the area between 19 and 20 be? If the area between 20 and 21 is 0.4772, between 19 and 20, same thing. Thank you. That's my area. I'm going to take 0.4772, multiply it times 2. Something like 0.9544. I really hope there's an answer up there. Addendum. The feeling of relief when the answer we calculate is actually on the key here, tremendous. Time to do it again. Question 8. And 9, we're both talking about something similar. Hey, we're maybe even talking about the same thing in number 10. We're starting to see, like I mentioned earlier, the same scenario pops up in problem and problem. And we've seen that already, talking about SATs, talking about Applewood. Monday, we talked about those 1183s. But here, the Office of Student Services at a large Western State University maintains information on the study habits of its full-time students. Their studies indicate that the mean amount of time undergraduates study per week is 20 hours. The hours studied follows the normal distribution with a standard deviation of 6 hours. Suppose we select a random sample of 144 current students. Thank goodness it's 144 current students. What's the standard error of the mean? Well, that one should be a little easier. How do you calculate standard error? Something over something. Katie. Sigma over square root n. What's sigma?
6.
Is it 6? Cool. What's n? Nope. How many students? How many observations? How many people in our sample? 144. What's the square root of 144, Katie? 12. So if sigma is 6, which it is, and my sample size is 144, 6 over the square root of n, 6 over 12 means the standard error of the mean is 0.5. Woo! It's up there. 8 down, 41 to go. Number 9. The Office of Student Services, etc. Now we're asking the question, what is the probability that the mean of this sample is less than 19.25 hours? We now have a population mean of 20. We have a sample mean of 19.25. My sampling error should be my sample mean divided by my my sampling error should be my sample mean divided by my say this right. My sampling error should be my sample mean minus my population mean. So negative 0.75. We're going to divide negative 0.75 by 0.5, which is our standard error, because our z-scores are sampling error over our standard error. Only one of those actually makes sense. So let's go ahead and execute on that. We know that the population mean is you should be studying 20 hours a night. I don't know, 20 hours a week? 20 hours a week seems low. 20 hours a week seems right. With a standard deviation of 6. Our sample mean is 19.25. And our sample size is a nice round 144. In the middle here is 20 and its z-score is 9. And the question is asking, what's the probability that the average number is less than 19.25? That's what the question asks, right? It's less than 19.25? Yeah. So we just need to follow the same steps. Or what, I don't know if it's a probability, a proportion, or a percent. So what percent of students study less than 19.25, or what's the probability? Effectively, we're answering the same question, no matter how it's asked. But I know I got to turn this raw score into a z-score. I'm going to take that z-score to my z-score table to find the area. Use that area to come up with whatever that is left over. So I'm guessing is 7%.
score.
What's my z-score formula? 5 or 6 words, please. Tiffany?
Sampling error.
Sampling error over standard error. Wonderful. What's my sampling error in this case, Tiffany?
-2.25 minus 20.
Otherwise known as
-0.75.
-0.75. 19.25 minus 20. That's how we find 0.75. Standard error we computed in the last problem to be 0.50. 3/4 over 2/4 seems like 1.5 as a z-score. Is my z-score 1.5? Yes or no, and why? Katie.
-1.5.
Thank you, Katie. -1.5. Z-score table, 1.5 gives me an area of 0.4332. 0.5 minus 0.4332, or approximately 7%. Some of these problems I'm moving through with a bit of pace, and then I try to give you a little time to catch up, write down, take a breath. It's always available online if you need it. But I do like to do a bit of a pace check to find out where we are. Too slow, just right, too fast. Where are we for pace? Because we do have another 40 questions to go. I don't know if we're going to be able to get through all of them because I believe the fashion police are in here at 7:30. No, Fashion Club, PC Fashion Magazine, something like that. So we can't stay for 2.5 hours, but we can continue at this pace or we can speed up a little bit more so that we can continue to work on more of the problems. Speed it up. Speed it up. All right. We're going to pretend the record's at 78. No one? All right. By the way, less than 19.25 means we need to do the tail of that distribution because it was less than. A10. The IQ test scores for adults are normally distributed with a mean of 100 and a standard deviation of 15. What is the probability we can select a sample of 50 adults and find the mean is less than 95? So the first thing we need to do in this problem is so very neat and clean. Pull out the essential information. I want the symbol and the value. And see if we can go efficiently. All right. Starting from the beginning. What's the first symbol we encounter and what's its value? Drew, yes, please. Mu is 100. Keep going. I need a symbol. Sigma equals 15. N equals 50 because it's 50 people. What, Chris? Is? Yep. So this question gives us those 4 pieces of information, which tells us the average is 100, but we're going to find 50 adults and want to find the mean of that sample of 50 is less than 95. So with those 4 pieces of information, we also know that it's normally distributed. Look at that, 4 pieces of information. And the mean goes mu, and I know mu is 100 because next to mu it says 100. I know that x bar, the sample mean, here should be 95 because next to x bar it says 95. I know the process I need to follow is taking some raw score, in this case 95, converting it to a z-score using a formula. Then I'm going to go to a table to get an area, and I'm going to have proportion probability percent left over at the end. And I need to be, according to the question, we need less than 95. Question here says less than 95, so less than 95, this is what I need. My z-score equals sampling error over standard error. What's my sampling error? Sampling error, sampling error, sampling error. Megan, yes, please. Thank you. -5, because 95 is 5 points below the population mean. And my standard error, sigma sub x bar, should be sigma over square root of n. Sigma is 15 because it says so right there. N is 50 because it says so right there. I'm going to guess we get something that's approximately 2. Standard error is 2.12. So -5 divided by 2.12 should give me something about -2.36. So my z-score, -2.36. Okay, that's a pretty small z-score. I come to my z-score table where it says, oh no, I don't have negative z-scores on here. It's been a while since we heard that one, right? Don't worry, it's symmetrical. So 236, 0.4909?
Yep.
Yeah, means this area is 0.4909, which means this probability left over in the tail can't be much more than 0.0091, or approximately 1%. That seems, oh, it's an option that's available, good. Oh, what a relief. But doesn't that seem like a z-score with a large magnitude? And it is. But what we're asking about here is like one of those examples that we may have seen at the end of last week with Coach Z. And Coach Z has a pretty large sample. And while Coach Z's classroom of 120 people did not move very far, they were only 50 points above the mean, where the standard deviation is 300. They had a pretty small sampling error. But because the standard error was also small due to the large sample size, a small difference meant a lot. In this case, it may only be 5 points. That group of 50 people averages 5 points below the mean. But in order to get a group of 50 people to average 95 or less, you need a lot of people to consistently be below average. That's a small standard error as a function of a pretty large sample size. 10 down, 39 to go. All right, so now let's talk about some concept questions. Number 11, Bones Brothers and Associates prepare individual tax returns. Over prior years, they maintain a variety of blah, blah, blah. They want to know how long it takes to prepare a return. I like to know how long it takes to prepare the extension form. Also, if you fail to report income, it takes a lot less time to fill these out. So that's a pro tip to all you kids in accounting right now. If you don't report income, instant. The mean time to prepare a return, I suppose if you report all sources of income, is 90 minutes. And the standard deviation of this distribution is 14 minutes. And I would call those mu and sigma because it's this huge, it's not a sample of a couple hundred, it's all this years of preparing the stuff. So I'm going to call mu 90 and sigma 14. Suppose 100 returns, sounds like a sample size to me. Suppose 100 returns from this year are selected and analyzed regarding the preparation time. What assumptions do you need to make about the shape of the population of all possible tax preparation times to make inferences about the mean time to complete a tax form? Well, we could either, oh, by the way, There should be apostrophes between these N's and these S's. That's disgusting. I'm sorry. I absolutely know that's a function of using Sakai as an HTML markup editor. Apostrophes don't always work nicely. There should be apostrophes here. My bad. But these 4 options. Do you need to make any assumption about the shape of the parent population? Do you have to assume that it's normal? Or make some assumption that it might be positively or negatively skewed? Those skewed ones might sound a little off to me. Why would you ever make the assumption that a distribution is skewed? Process of elimination, I get rid of A and C for you. Who says B? Bravo. You have to assume the parent population is normal. Who says D? Delta. You don't have to make any inferences about the shape of the distribution. So that's our answer. It's going to be D. And that's that corollary of the central limit theorem. Actually, I think it's not even the corollary. It's what the central limit theorem says. If you take a sufficiently large sample size of any shaped distribution, the distribution of sample means is normal. And what we're asking about in this case is a sample of 100 observations and the mean of that sample 100 observations. In the language that, James, by the way, I'm co-opting your language when you were talking about those means gravitating, the sample means, the blue dots, gravitate towards the population mean. I kind of like that language because that's a situation like we have here. Whatever shape the parent population is, this mean is where most of the collections of observations are going to show up. This mean is the population mean. So most of the sample means are going to end up near that regardless of the shape. Because if the population mean is 8, ignore anything about the shape of the population. If you take a large enough sample size, your sample mean should also be 8. Might be a little bit above, might be a little bit below, but that sample mean should probably be pretty close to the population mean. You don't need to make any assumptions here. All right. 12, true or false? Sampling a population is often necessary because the cost of studying all the items in the population is prohibitive. True or false? Who says true? Who says false? If you didn't raise your hand, earmuffs because you don't deserve the answer. Who says true? Who says false? The truths have it. Oftentimes we need to sample because if I wanted to observe everyone in the population, that would be impossible. It's just physically impossible. It also costs a lot of money. I just got a bill this morning for 430 people filling out a 15-minute survey. It cost me $2,300. So sampling 400 people is a little cost prohibitive. I don't even have my wallet in my back pocket anymore, or it's that thin. No, it's expensive. 13. When doing research, knowing the population mean and the population parameters is essential. Who says true? You got to know that stuff. Who says false? You don't have to know that stuff. So the answer is false. We're often making inferences, and that's where we start. The first half, when we're talking about any sample statistics, those are all descriptive statistics. But now we're going to start making inferences about those population values. Now, please note that if I do have mu or sigma or pi in these problems, it's not that I actually know the population parameter. It's that those things are expected values. They're values which I'm told. Is that I look at the bottle and the bottle says 20 ounces, so I expect 20 ounces, and then my observation might compare to what I'm told. 13 down, 36 to go. 14. If the size of a sample equals the size of the population, we would not expect any error in estimating the population parameter. Who says false? Who says true? Yeah, trues better have it. This is the circumstance when I believe that I'm observing the entire population. So Must be good. Skip one. Don't think so. 15.15. We can expect some difference between sample statistics and the corresponding population parameters. This difference results from the procedure of sampling and is therefore called sampling error. Who says true? Yeah. That's called sampling error because we did sampling. 16. A sampling distribution of the means is a probability distribution consisting of all possible sample means of a given sample size selected from the population. What'd you say, Chloe? I think it's true too. Do you know why it's true?
No, the thing that makes sense is the sample that corresponds to the population.
It's a sample which corresponds to the population. Anybody else flesh out this answer? So the short answer is that it's the definition. The longer, I don't know, Pareto solution is one that's more like this. These are sampling distributions of sample mean for sample size 2. This is a sampling distribution of the sample mean for 25. We're able to illustrate them as empirical probability distributions because it's a simulation where I take a sample of size 2 and a sample of size 2 and a sample of size 2. It becomes something where I've collected data. But if we go and look at the bigger picture, what an actual sampling distribution of the sample means would be all of the possibilities. Sure, 100,000 reps is a lot, and 1,000,000 reps is a lot too. Maybe all, maybe close to all, but if we're really talking about, strictly speaking, what the definition is, it's all possibilities, and it's for a specified sample size. And that's the other part of the definition of the sampling distribution, the sample mean, which is important, is that it has to be for a specific sample size. For this population, this is the sampling distribution of the sample means for sample size n equals 2. For this population, this is also a sampling distribution of the sample mean, but it's for sample size 25. So it depends on whether you're talking about sample size of 2 or sample size of 25. But as Chloe said, the answer, true. 17.17. If the sampling distribution of the sample means approximate a normal distribution, then the population is normally distributed. So I don't know if I like distributed or distributed better. Let's see how your injections, bijections, and conjectures go here. James?
I think it's false because central limit theorem says that the sample distribution is going to be normal regardless if it's positively skewed, negatively skewed, normally skewed, or equal to x.
Yeah. So this really only goes one direction. In fact, always, if you have a sufficiently large sample size, always will the sampling distributions of the sample means approximate a normal distribution. Always. So if it's constantly normal, it gives you no predictive power about what the shape of your parent population would be. I like it, James. Good work. The mean of all possible means is the population mean. The mean of the means is the mean. Let me hear you say yeah. Let me hear you say yeah.
Yeah.
Either I would be a horrible musician or you would be a horrible audience. We would never be able to do that. Let me wave your hands like you just care. Stuff like that. We'd never get done. In the sampling distribution of the sample means. Question 19. You did 18. Do we skip one? No. The mean of the means is the mean. 18 is true. I heard you say yeah. 19. In the sampling distribution of the sample means, the standard error of the mean will vary according to the size of the sample. As the sample size n gets larger, the variability of the sampling distribution of the means gets larger. False. Why false? Isn't it, couldn't even be sometimes true? Mm-mm. Mm-mm. There's a lot of words in here which we could break down. What one word could you switch to something else here, Stephen?
Instead of gets larger, it gets smaller.
Yeah, we all want to change this word right here. So here's the story. In the sampling distribution of the sample means, so in the blue dots, the standard error of the mean, which is its variability, will vary according to the size of the sample. Sample size of 2, sample size 25. That statement is true. We know that with sample size of 2, wide, sample size 25, narrow. As sample size n gets larger, the variability of the sampling distribution, variability like variance, variance like dispersion, dispersion like standard deviation. As the sample size gets larger, the standard deviation of those blue dots gets larger. It's the other way around. It's inverse relationship. As n gets bigger, standard deviation of the means gets smaller. The central limits theorem states that if the sample size n is sufficiently large, I like that expression, the sampling distribution of the means will be approximately normal, even when the population is skewed or uniform. Yeah, true, true indeed. I can make this uniform. And with sufficiently large sample size, it doesn't matter what my population is, my sampling distribution of the sample means will in fact be approximately normal. 20 is true. 21. For the sampling distribution of the sample means, sampling error will decrease as sample size increases. Sampling error, x bar minus mu. Sample size, n. What do you think here? Curry.
I think it's true.
Why?
I think that the larger sample size, less error.
Larger the sample size, the less error. Sampling error or standard error? One of those is a mathematical proof. Standard error does get smaller when your sample size increases. But what happens to sampling error if your sample size is the same as the population size? Sample size and population size are the same. Is there sampling error? No. So while it's not a direct outcome of the mathematical expression for sampling error, increasing your sample size means you get more accurate because you're decreasing the variability in the sampling distribution of the sample means, yeah, sampling error will decrease. You're more likely to get an accurate response. Let's call it true. 22. You know what? I'm skipping 22. I'm not even bothering 22. If you need me to answer 22 for you, I don't want to. 23. The standard error of the mean measures the dispersion of the sampling distribution of the sample mean. What do we say for 23? I know you're leaving, Samantha. Prove to me you're here. 23, true or false? Sure? No. All right, well, you're lucky. That was a good, decent guess. Yeah, true. 23 is true. That's exactly what the standard error is. Sigma sub x bar, the variability in the sample means. The standard error, sigma sub x bar, is the dispersion of the sampling distribution of the sample mean. how wide those blue dots are. (24) What's the difference between a sample mean and a population mean called? 1, 2, 3. Sampling error. All possible samples of size n are selected from a population, and the mean of each sample is determined. What is the mean of all possible sample means? Above population mean. Good. Hey, we're more than halfway there. Is that why everybody's leaving? Trying to get to break before it closes. You just got better things to do? Just want to break my heart? That's all right. Good to see you guys. Thanks for stopping by. The rest is available online. At least I hope it is. Did I hit start? Oh, I didn't share the link though. I'm gonna share the link. Hey, everybody staring at my face because I forgot to share the link. Just hanging out. Sorry, and everybody else, module 8, homework help link. No salutation, no sign off, no context, just a link. Call me a hypocrite. 26. The true sampling error of the mean is usually not known because why don't we usually know true sampling error? There are two things we need to know sampling error. For example, sample Katie. Yeah, because we don't know mu. We need sample mean and population mean, but rarely, if ever, do we actually know the true population mean. So true sampling error is hard to find if we don't have mu. Good work. Thanks, Katie. 26 down, some more to go. 27. The mean of all sample means is? Want to say it together? 1, 2, 3.
Yeah.
Try it again. 1, 2, 3.
Yeah.
Wait, now you're changing. No, I just wanted to make you guys sound like cows. Because if you got a bunch of people going moo, sounds like back on the farm. All right, never mind. None of y'all ever get homesick? Because I grew up on a farm, okay? Shut up. As the size of the sample increases, what happens to the shape of the distribution the sample means? The shape of those blue dots, what happens as n gets bigger? Yeah, going back to what Chris said earlier, d delta becomes more normal. According to the central limit theorem, now here's a tasky one because central limit theorem says some things directly, but some parts of the central limit theorem are corollaries. Corollary being sort of like a, because we know this, an obvious follow-up conclusion is this. We'll call that a corollary. In mathematics, they're very specific. But in this case, a lot of these things are known to be true, and increasing the sample size decreases the dispersion of the sampling distribution of the sample means. Like that thing's true, but the sampling distribution, that one's not true. The population mean, the mean of all sample means is equal. That one's true as well, but question 29 is asking you which one of those is true according to the central limit theorem. Means C is true, D is also true, A is also true. Is C what the central limit theorem states specifically? Yeah, I don't know either. James?
I would say it's A, just because it makes like it's it uses the most like it's not. I don't even know why. Just A.
Katie?
I would say A because central limit theorem states that using samples allow us to
Okay. But that would mean less about decreasing the dispersion and more about Drew. Where are you going?
D.
I would go D here. And so based on what Katie just said there, the reason we can use the Z table, which is a table for normal distributions, the reason we can use that is because of the central limit theorem. And we can only use the Z table if we're operating under a normal curve. We can either operate under a normal curve if our population is normally distributed, or there's some intermediary between your population of whatever shape and something to do with sample means. And that intermediary happens to be the central limit theorem. This is a tough one. I'm going to tell you the answer is D. But know that we haven't, in our classes, gotten super preachy about exactly what the central limit theorem is. I really want you just to have a functional working knowledge of, thank you, central limit theorem. You tell me all of this nice stuff. This is the first and most important thing. It allows us to have normal distributions. But given the amount of time we have left, and only 20 questions, we're actually proportioned about the right pace here. Knowing that parts 2 through, right, by the way, call 29D, tell this. Part 2, part 3, part 4, part 5, part 6, all work under the same conditions, and those parts are identified at the top. So for part 2, mu is 75, sigma is 5, n is 40, which means the standard error for all of these cases is 5 over the square root of 40. The square root of 40 is 2 times the square root of 10. Doesn't really help me there. No, that's not a good fraction to deal with. But we're still, for all of these questions, effectively doing the same thing. Starting with mu, sigma, and n, which is the population mean, standard deviation, and a sample size to give me a standard error. And then I'm going to compute z-scores for this raw score, for the next raw score, and the next raw score as sampling error over standard error. And standard error doesn't change. So for question 30, less than 74. For question 31, between 74 and 76. For 32, greater than 77. And for 33, between 76 and 77. Let me point this out again, but visually. We have a mean of 75, sigma is 5, n is 40. What's the standard error here? Just sigma over square root of 40. Chris? 0.79?
Yeah.
So for whatever we're calculating here, for this whole array of different sampling errors, our standard error of 0.79 stays the same. And in the case of all of these different questions, less than 74, between 74 and 76, greater than 77, between 76 and 77, we're going from a raw score to a proportion. We get there by converting the raw scores to a z-score, taking those z-scores to the table to get an area, and so on. So if I wanted to be efficient, and I want to, I would put mu of 75 in the middle. I know that I have a raw score of 74 that needs to be converted to a z-score. I have a raw score of 76, which needs to be converted to a z-score. A raw score of 77, which needs to be converted to a z-score. Because question 30 says I want less than 74. I know that question 31 says between 74 and 76. I know that 32 is greater than 77. I know that set 33 says between 76 and 77. So I can actually attack this problem with a bit of efficiency just by knowing that, hey, I've got this piece, this piece, this piece, and this piece. Those are the 4 pieces I need to figure out. That's going to come from 1, 2, 3 different z-scores. In fact, what do we know about the z-score for 76 and 74? Brendan? All right, what's the z-score for 76? The z-score for 76.
1.27.
Confirmation on 1.27? I see a thumb. Which means this one is probably negative 1.27. That's the second time I said 7 and wrote 5. That's weird. How did I get here? Because my sampling error was 1. And I took 1 divided by 0.79. If I double my sampling error from 1 to 2, and z-score is sampling error over standard error, and I double the numerator of my fraction, what happens to my z-score? I've changed my sampling error from 1 to 2. I've doubled my sampling error. What do you suppose happens to my z-score? Doubles as well. So this looks like a complicated 4-part problem, which I'm going to say that's probably I'm going to say 3, based on rounding. Or you can call it 2.54. Probably 2.53, given the rounding. We don't have that much further to go. I go to my table to find out what these other areas are. So here, I need a z-score of 1.27, 0.3980, 0.3980. All right. So what's the answer to 30? Probably 0.5000 minus 0.3980. What's the answer to 31? I'm going to add those 2 things together. What's the answer to 32? Well, I need to find 33 is the hardest one to calculate here. 33 just says 2.53. All of this whole mess right here, .4943. So the answer to 43 is 0.4943 minus 0.3980. And 32, this little sliver right here, 0.5 minus 0.4943. That's definitely introducing something new that you haven't seen before. Because normally I've gone through these problems one at a time, step by step, R to Z to area to P, and back. However, I just did 4 problems all at once. But that's just the 4 different ways that you can carve up these things. Taking a tail, adding 2 things which are on the opposite side, subtracting 2 things because the 2 areas are on the same side, or again, finding a tail. provided I remember the direction of all of those correctly, which is less than 74, greater than 77, between 74 and 76, and between 76 and 77. I'm not going to do the arithmetic, because arithmetic is boring. You guys got calculators? Questions on those 30 through 33?
What was the answer to 31?
Oh, I don't know. Looks like,
Would you just add the two together?
yep.
Okay.
So probably something around 80%, 79.6%.
Okay.
Is there something in 31 that says that?
Yeah, 0.7924.
Yeah,
Okay. Thank you.
it's pretty close. Oh gosh, and it's the only one that makes any sense at all there. I mean, that could possibly be the case, but it seems pretty ridiculous that it would be. Can't have a negative area, can't have an area more than one. It's got to be one of those two. That's a little small. So we're going to do the same thing with part 3. According to an IRS study, it takes a mean of 330 minutes for taxpayers to prepare, copy, and electronically file a 1040 tax form. Where are my accountancy majors at? Really? I mean, I know some of you are finance majors because you're my advisees, but no one here is doing accounting? Has anybody ever filled out a 1040? You guys know you have to like do your own taxes and stuff, right? No, I'm just saying you might all be criminals, and then I'm wasting my time on a bunch of people who are going to be unemployable because you're all in jail for tax evasion. Do your taxes. If you don't, I won't. The distribution of times follows the normal distribution of the standard deviation, 80 minutes. A consumer watchdog agency selects a random sample of 40 taxpayers. So we're really given 4 bits of information here. The 4 bits of information are what? Give me one. Give me one, give me one, give me one.
Maybe it's 330.
What else you got, Katie? Give me 2, give me 2, give me 2.
Standard deviation is 80.
Give me 3, give me 3.
And it's 40.
You know what the 4th piece is?
But it's normal.
Normal. Now, Steve, let's talk about my friend and yours, the standard error. What's the value of standard error?
12.65.
Square root of 40, something like 6-ish. Yeah, 12 sounds about right. What'd you say, 12.65? Yeah. Which is something like 12.649, which is really close to 12.65. But it's definitely not 12.5 units. And if we're going to talk about means of sample size 40, you can draw a really shoddy normal distribution. Looks like it's going to choose you to be part of Gryffindor. I could probably use, what's the standard error? Hey, 34, the standard error is 12.65. Sounds good. And then we've got a series of difference, 35, 36, and 37. In 35, we're looking for greater than 320. So I'm drawing 320 on my picture. For 36, I'm drawing 350 on my picture. For 37, I got to get between these two. So for 35, we're saying greater than 320. 36, we're saying greater than 350. And for 37, we're saying between 320 and 350. But effectively, we're doing the same thing we did before. But in this case, note not to scale. Sampling error 10. Sampling error 20. This z-score is not the same as this z-score. But once I find out this z-score, which is something around 0.85, what is it? Trying to do math in my head always gets me in trouble. 0.79? 0.79, Christine?
Negative.
All right, thanks. Take that. And we get there by saying our, so this z-score is the sampling error divided by the standard error, which is negative 10 divided by 12.65, which is negative 0.79. And then if you do this one, it's going to be 20 divided by 12.65. So it gives me something on the order of 1.58, 1.59, 1.58. Raw scores to z-scores. Z-scores to areas. So with a z-score of negative 0.79, I believe I'm going to find 0.2852. For a z-score of 1.58, I find 0.4429. Greater than 320. I'm going to have to add or subtract something to find the answer to 35, to find greater than 320. What am I going to add together to find greater than 320? Katie?
0.5.
Plus?
0.2852.
Sounds good. If I want to find greater than 350, what am I doing for greater than 350? Katie? I like pointing at people and saying Katie. It's fun.
0.5 minus 0.449.
Yeah, so in this case, we're going to have to find a tail. So we're going to take 0.5 and subtract. In this case, we're going to take 0.5 and add. Hey, Chris, how do we get between 320 and 350?
Yeah.
Yep, we're going to add those two together. Three more.
Will the link be up on Clickback?
It is now.
Will it be out there still for us to see after or just?
Oh yeah, no. This live streams and then it's archived to my YouTube channel.
Okay.
Yep.
Thanks.
Yep. Am I outrunning you, Sharon? Or you gotta take off?
I do have to go. I next class.
10-4. Thanks for stopping by.
Work.
Part 4. Department of ED. So the Department of ED at your university, student records suggest that the population of students spends an average of 5 hours per week playing organized sports. The population standard deviation is 2.2 hours per week based on a sample of 121 students. Healthy Lifestyles Incorporated, HLI, would like to apply the central limit theorem to make various estimates. Thanks, Drew. Boy, am I happy that they took a sample of 121 students, especially since the standard deviation is 2.2. Standard error is going to be 2.2 divided by the square root of 121. 0.2. Now I have a really, really nice standard error to work with. Before we go diving into this part for part 4, standard error. Once you start getting used to taking standard deviation divided by square root of sample size, you start to see how big meaningful differences are, and you can spot them right away. Standard error, the mean's 0.2. We got 38. Sample mean between 5 hours and 6 hours. Look at these choices. Between 5 hours and 6 hours. The central limit theorem tells us that the distribution of sample means will be normal. And we assume that the mean is going to be 5.5 because that's what the records say. The mean is 5.5 and the standard error is 0.2. What's the answer to this question? Look at the possible answers before trying to figure out what the answer is here. Why? Because that's a big number. That one isn't big, that one isn't big, that one isn't big. We're saying given a mean of 5.5 and a standard error of 0.2, well, geez, 2 standard errors in either direction gets me to 5.1 and 5.9, and that should be approximately 95% of stuff. And I'm a little bit further out than that. It should be something on the order of 95%. How strange would it be to obtain a sample mean greater than 6.5 hours? Very likely or very unlikely? James, talk to me.
Very unlikely because the z-score would be over 3.
Yeah, over 3. It'd be overboard. Actually, no, it would be about 3, wouldn't it?
I think so, yeah. Yeah, no, it'd be like
6.5 minus 5.5 is 1 divided by 0.2 is 5.
yeah, so
5's a big z-score. In other words, a sample mean of 6.5 hours is 5 standard error units above the mean. That's a lot of standard error units. Standard error, sigma sub x bar, is just like standard deviation, except we're talking about sample means. And in this case, the sample size is 121. 121 is a pretty sizable sample. So if you're told the average is 5.5, with that particular standard deviation 2.2, sample 121 people, you don't need a very large difference to have an expectation that's just different from what you're told. What do you suppose the probability of the sample mean will be between 5.3 and 5.5 is? Let me see if I can get a new voice on this one. I want somebody else to tell me that they know what's up. Leah, I haven't heard yours today. Good morning. No? Okay.
I would say 15.
Which is what value?
68, 68.
About 68%? Why, when I hear 68%, it's the empirical rule which comes to mind. And that says if I'm at the mean of a normal distribution, I can go 1 standard deviation below, 1 standard deviation above, and get about 68% of observations in here. Tell me a story here. I'm going between 5.3 and 5.7. What's in the middle of 5.3 and 5.7? And what do we know 5.5 is? The mean. So if I go out from 5.5 to 5.3, how much is that? 0.2, and 0.2 is also in this problem known as? Yeah, it's the standard error. So we're going one standard error unit below and one standard error unit above the mean which is given to us. And that works just like the empirical rule, because the central limit theorem tells me the sampling distribution of the sample mean is going to be approximately normal given a sufficiently large sample size, and 121 is certainly a sufficiently large sample size. So the central limit theorem means I can use the empirical rule, provided I've got a big sample size, which I do. I don't mind saying it. And I go one standard error below, one standard deviation above, one standard error above, 68%. Part 506, Power Plus Incorporated produces AA batteries used in remote control toy cars. The mean life of these batteries follows the normal probability distribution with a mean of 35 hours and a standard deviation of 5.5 hours. As a part of its quality assurance program, Power Plus Incorporated tests samples of 25 batteries, which seems very odd to me because if you've ever used batteries, you know that you usually have to use them in pairs. Very infrequently do I use batteries on their own, or AA batteries, or whatever you call them. We have samples of sample size 25, and I go, yes, because 25 is a square number. Square root of 25, Billy? What's the standard error then? 1.1, because it's a standard deviation of 5.5 divided by 5. 5.5 divided by 5 is 1.1. My standard error is 1.1. Is that the first question? Yeah. Are you used to standard error being the first question? You should be. What can you say about the shape of the distribution of the sample means? Hey, normal. Sounds good to me. What proportion of the samples will have a mean useful life of more than 36 hours? You know what? This is a case where I'm actually going to use the paper. So I haven't written anything in a while. I think I need to slow down. In this case, mu is 35. Sigma is 5.5. N is 25, which means standard error is 1.1. But question number 44 says, what proportion of samples will have a mean useful life of more than 36 hours? $35 is the raw score mean. We got to do greater than 36. Z-score for the mean is always 0, and yes, I'm sure. I go from a raw score to a Z-score to an area to a proportion percent. I don't know. Which do you prefer? 5 or 6 words to calculate the standard error of the mean? I prefer 5 words. But you could prefer 6. Phil, what do you prefer? What are those 5 words? Oh, that's 6 words. You like divided by, I like over. Either way, we're still taking exactly what you said. So in order to find the Z-score here, we need sampling error over standard error. What's the sampling error here? What'd you say, Phil? How about this one? So my sample mean is 36. The expected mean is 35. So what's my sampling error? 1. Thank you. Sampling error is 1. My standard error is 1.1. 1 divided by 1.1. Katie?
0.909.
90909090909090909. All right. Sorry. Gotta hit the reset button every now and then. Z-score of 0.91. Z-score of 0.9090, sorry, 91. Gets me an area of 0.3186. And so I say 0.3186. And I casually move on to the next problem because this is me being casual. Jack, am I being too casual? Maybe. Let's take a look at where I went wrong. I felt a little too casual there. I found the area here to be 0.3186. I want to know the probability that they'll go longer than 36. How do you go longer than 36?
You subtract 0.3186 from 0.5.
Yeah. So don't be fooled by an answer such as this. Because what we really need is 0.5 minus that, which is 0.1814. We got 45 and 46 to do here. We got to get a sample mean with a mean useful life greater than 34.5. Ooh, that's an ugly vertical line. And then for 46, we have to get between these two. So this is going to be, for number 35, we're going to do greater than 34.5, and for number 36, we're going to do between 34.5 and 36. So if the z-score for 36 is 0.91, because its sampling error is 1, what's the sampling error associated with 34.5? Sampling error here is 1. Sampling error here is, Connor, do you know this one? Yeah, that'll be the z-score. But what's the sampling error here? The sampling error here is 1. Yeah, 0.5. And then 0.5 divided by our standard error of 1.1 is half of 0.09090909, which is 0.45454545454545454545. Maybe. Is that right?
Yeah.
All right, cool. We come to our table, look for a z-score of 0.45, 1376, 1736. Now I'm reading 7s and 6s, right? 5s and 7s. So greater than 34.5 is going to be 0.5 plus 0.1736. Between 34.5 and 36, 1736, 3186. I think that's like 0.5 and change, right around 0.5. Maybe just a bit under. Yeah. Greater than 34. Something around 67%. Between these two, Is it going to be 4922 or 5078? It's got to be one of those two. But I think 6 plus 6 is 2. So I'm going to guess it's this one. So I'm too lazy to actually carry the 1. It's heavy. It's a big one. It's a heavy one to carry. 46 down. 3 to go. 4 minutes to spare. So, wow, that's a weird looking answer. The mean amount purchased by a typical customer at Church Hill's grocery store is $23.50 with a standard error of 5, counting $5. Assume the distribution of amounts follows the normal distribution. For a sample of 50, that's 50 customers, answer the following questions. What is the likelihood that the sample mean is at least $25? All right. We're going to have a population mean, a standard deviation, a sample size. With the standard deviation and sample size, we're going to combine them to create standard error. Take that. And we'll use 25 as a raw score. Take 25 minus 23.5, and we'll get a sampling error of 1.5. And you can take 5, the standard deviation, divided by 7, which is the square root of the sample size, you'll get a standard deviation of something around 0.84. 25 minus 23.5 is a sampling error of 1.5 divided by 1.8, sorry, just 0.84. It's going to get you something around 1.3 and change. So I'm going to guess that our answer is somewhere around, I'd say that one. That's just a guess. Let's actually do it, though. I don't like guessing. So in case this problem, we have the Churchill's grocery store. Mu is 25. It's normally distributed. Sigma is 5. N is 50. No, sorry, mu is 23.5, right? $23.50. Somewhere over here is 25, and those are raw scores. In the middle is here, and I got to take this raw score of 25 and convert it to a z-score. What's my standard error? Looks like 5 divided by square root of 50. Yeah, Chris, it's been a while. 170.707. No, it's 0.71. How about 0.71? Or 707, actually, it should be 707. We're going to use the calculated z-score, which we want to 2. Z-score, and I'll save you the trouble here. Sampling error over standard error. In this case, sampling error is $1.50. The standard error is 0.707. Oh, I did a bad job calculating standard error. I did a really bad job calculating standard error. Oh, because 50 over the square root, sorry, 5 over the square root of 50 is not 0.8, it's 0.7. So 1.5 divided by 0.707. You did it right. I did it wrong when I was doing it in my head. I did it wrong. You did it right. Don't you freak out. You have calculators. I have as much as I can. At this time of night or morning. What? What's my z-score, Mike?
2.12.
2.12. That's an awfully large z-score. Z-score of 2.12, I find an area of 0.4830.
What is the point two up
Say what? Say what?
there?
I don't think so.
I did 0.7 or 7.07.
Yeah, our standard error is less than 1. And we've got a number bigger than 1 divided by less than 1. It should be bigger than that.
I did 7.
Oh, okay. Yeah, no. Still all over the place. But 2.12 is our z-score. Area 0.4830. And in the question, we are asking, what's the likelihood the sample mean is at least 25? So 25 or more is at least there, so probably something around 2%. And by the way, that answer is actually on that sheet. So there's your answer, 47. 48 now asks the question, what is the likelihood the sample mean is greater than 2250 but less than 25? 2250 less than 25. Question 48 is asking for that in its entirety. This sampling error is 1.5. This sampling error is 1. So I would probably take 2/3 of 2.12 to find out what this z-score is. I'm going to guess it's on the order of -1.4. Anybody able to take sampling error over standard error to tell me the z-score for $22.50? Katie? Katie's? 1, 2, 3?
21.41.
I got different answers. Try it again. 1, 2, 3?
Negative.
Ah, that's where we got to make sure we're aligned here. Gonna start at the same time and end at the same time. -4.1. That helps us. -1.41 helps us out quite a bit. What you got, Steve? 204, 207?
Yep.
Therefore, number 48. 4207 plus 4830 should be something on the order of 90%. Hey, here was that 2% we saw before. Here's the 90% we see right now. Question 49 and 49. Within what limits will 90% of the sample means occur? We're basically coming full circle back to that first one that threw people for a little bit of a loop. This one says we are normally distributed around a mean of $23.50, and we want to capture 90% of stuff. If we're going to capture 90% of stuff, that's a proportion, which we need to work to an area, which we're going to work to a z-score, which we're going to work to a raw score so that I can find out what those two raw scores are. I got to use my picture to get from a percent to an area. What area do I put here? Okay. I like these 4 digits, so I can look it up in here. But I cannot find 0.4500 in here, so I got to choose one of those. You could choose 1.64, you could choose 1.65, or in this case, 1.645 is the correct choice. In this case. Halfway between those two, the special point in the distribution. So now I've worked from those areas of 0.4500 to z-scores, so plus or minus 1.645. And the last thing I got to do is say my raw score equals mu plus z sigma, where mu is 2350. Z is 1.645, and that's the standard error, by the way. The standard error in this case is 0.707. That's really far more precision than we actually need because it's a multiple choice answers with sufficient distance between the options. What do we get for our margin of error here? Oh, I'm sorry. Spoilers. Yes, that was my River Song impression, by the way. 1.645 times 0.707. Anybody help me out with that one? Or do you want me to struggle through multiplication in my head with that many decimals? Mike? What's that?
1.16.
Do I get confirmation on 1.16? Yeah, that seems about right. $1.16. So $23.50 plus or minus $1.16 is going to set my bounds to $21.34 and $24.66. And hopefully there's something around that. I mean, around $22.34. Oh, subtraction. That looks more like $1.16 under $23.50. That 49. Sorry that it took us 6 minutes more than 2 hours. But hey, that's 49 problems. Good work, y'all. Mm-hmm.